For the introduction and for the invitation to give a talk here. So I will describe a joint work with Stanisław Szarek and Dépigné, and the topic is to understand the regime in which the quantum marginals are generically entangled. So let me first give an overview of the talk. So it will be a question of high dimension state. So this is the main question. If I look at the quantum marginals in large dimensions, when can I say that it is typically entangled? And we will see that this question is connected to some quantities which appear in convex geometry. So I will provide you some background on this. Then I will compute some quantities involving the set of separable states, so again in large dimensions. And I will try to explain that for this generic situation, detecting entanglement can be achieved by using a single witness. So I will try to explain this. And I will conclude with some related questions. So let me start maybe with a physical motivation or one vector of the problem. So assume that you have n qubits. So n is large. And these n qubits are in a in a global pure state. So this means that the state is described by a unit vector in the sphere in C2 to the nth tensor power. And when I say generic, I mean random, and this randomness is given by the Haar measure, the uniform measure on the sphere. So I take such a random state, pure state on n qubits. Now I split these qubits. I give some of them to Alice, so some of them to Bob, and forget about the remaining ones. So more precisely, let P be a number less than half, a proportion, and you give Pn qubits to Alice and Pn to Bob. And you take partial trace over the other ones. So if you do this, now Alice and Bob share a mixed state, and the question I want to understand is whether this mixed state contains some entanglement. So if you don't know what it is, I will define it at some point when it comes naturally into the talk. So let's first look at extreme cases for this problem. So first, if P is equal to 1/2, if you give all the qubits to Alice and Bob, nothing remains, so there is no partial trace, and what Alice and Bob actually share is a pure state. And as we saw this morning, a pure state typically is not a product vector, so typically this pure state will be entangled. At the other extreme, if P is very small, which means that the environment is huge, then we expect, because of decoherence, we expect Alice and Bob to share a state which will be very mixed, very close to be maximally mixed, and therefore it should be separable. So by looking at these extreme regimes, we expect maybe a phase transition between these two behaviors, and this transition should only depend on the relative size of the Alice-Bob subsystem with respect to the environment. So here is the answer for this problem. So it's our main theorem. So there is a critical value, indeed, so some threshold P0, which is equal to 1/5, such that in the limit when n is large, if you give to Alice and Bob a proportion which is slightly larger than P0, then they will share some entanglement. And if you give less than P0 proportion, they will not share any entanglement. So these statements hold generically, which means that the probability that they hold tends to 1 very fast, exponentially fast to 1, as n tends to infinity. And I will explain you that the value P0 equal 1/5, this critical value, will be related to some geometric properties of the set of separable states. Another point is that this threshold is sharp in the following sense. If you are slightly below this critical level, if you just give 2 more qubits to Alice and Bob, then it flips, the picture flips, and you're changing from one regime to another one. So only 1 or 2 extra qubits completely change the picture. Okay, so it's more convenient to measure local dimensions not by the number of qubits but just by the dimension itself. So it's just a switch of presentation. Now let's say that I give Alice and Bob a copy, each of them a copy of the space CD. So their joint space will be HAB equals CD tensor CD. And I will also denote by CS the space which corresponds to the environment. So if you connect with the previous model, Alice and Bob were given each Pn qubits, so D should be 2 to the Pn, and S, the environment, should be 2 to the 1 minus 2 Pn. And in particular, this value P equal 1/5 corresponds to S equal D cube. So in this formulation, the threshold will be when the dimension of environment is of order D cube. And just let me state again the problem. You start with a random pure state psi on the space HAB tensor CS. This random pure state is hard distributed, and you look at the quantum marginal onto AB, and you ask if it is entangled or not. So actually, today I will show only the easy half of our result. So we are two regimes. I will show that the entanglement is generic in the range when the environment is smaller than D cube. And to do this, we will show that the set of separable states is small in a sense to be precise. And tomorrow, Staszek Szarek will give a talk when he, in particular, he will cover the other range and show that separability is generic beyond this threshold. But I won't talk about this. Okay, so let me give you some information about this random quantum marginals. So let's forget for the moment that the space H is bipartite. Later, H will be equal to CD tensor CD, but for the moment, let me just call it H. So you have this quantum marginal obtained from a hard distributed pure state on the space H tensor CS. And you may ask what is the distribution of this random mixed state. So as long as the dimension of the environment is larger than the dimension of H, you will obtain typically a state with full rank. And the density, the probability density which describes the distribution of rho with respect to the Lebesgue measure on the set of all states has a very simple formula, which is determinant of rho to the power S minus the dimension of H. This was proven by Żyskowski and Sommers. So let me say two things. First, if you choose S to be equal to the dimension of H, you recover the uniform measure on the set of all states. And second, you see that the determinant function is maximal when rho has all equal eigenvalues. So you see that when S increases, this measure tends to be more and more peaked towards the identity over N. But this precise formula won't play such a big role in our proof. Something which will be more interesting for us is the fact that instead of starting with a spherical model, you may instead consider a Gaussian model. So if you start with G, which is a rectangular matrix of size dimension of H term S, and if you fill it with independent Gaussian entries, and if you compute GG star over its trace, you obtain a state which has the same distribution as before. Okay, so for us, H will be bipartite CD tensor CD. Okay, so I promised you some background from convex geometry, so let me introduce this classical fact. So the single bar denotes the Euclidean norm on Rn, and B2n will be the Euclidean unit ball. Now, if I have any compact convex set which contains 0 in the interior, K, and I can define what we call the gauge of K, which is somehow like a norm. The gauge of K at a point X is computed as follows. You look at all the annotated copies of K, and you look at the smallest one which contains X. So by which factor you have to enlarge K to contain X. And if K happens to be centrally symmetric, then this is a norm for which K is a unit ball. But typically, we'll consider non-centrally symmetric sets. So we will have this slightly extended notion. Now there's a duality notion for norms, and at the level of unit balls, it translates into what we call polarity. So the polar set K circle of a convex body K is defined here. It's the set of all the vectors in Rn for which all inner products with points of K are less than 1. So it corresponds to the duality for norms at the level of unit balls. And this K polar is quantity is -1 homogeneous. So if you enlarge K by a factor of t, the polar decreases by a factor of t. Okay, so I will compute volumes of convex body. So volume is simply the Lebesgue measure. Now, the Lebesgue measure is n homogeneous in Rn. So typically quantities scale on the like powers of n, and it's more convenient to raise everything to the power 1 over n to obtain something which is 1 homogeneous. And it's also convenient to look at this quantity Vrad, which we call the volume radius. So it's the volume of K over the volume of B2n, the Euclidean ball, raised to the 1 over n. So if you want, the volume radius of K is the radius of the Euclidean ball with the same volume as K. So how does this quantity behave with respect to polarity? So there is a couple of inequalities which precisely say this, which are called the Santalo inequality and the dual Santalo inequality. So here you see it involves the product of the volume radius of K and the volume radius of K polar. So this product is 0 homogeneous. So it could be it could be of order of a constant, but it's a remarkable fact that there is a couple of inequalities which hold as a lower and upper bound on this volume product, which are uniform with respect to dimension. So here, whenever you have any convex set in Rn, so we have the assumption that K as center of gravity centroid at the origin. Then this volume product is bounded above by 1 and bounded below by some absolute constant, maybe pi over 8. No. C is so I think pi over 8 works. So it's this is the point. If you want C to depend on n, it's much easier. Yeah. So and for us, what it means is that if you want to compute the volume radius of a set up to absolute constants, it's enough. You can dualize. You can compute the volume of the dual set. That's how we use it typically. So the upper bound is called the Santalo inequality, and it's quite old. And it's sharp, of course, if K is the Euclidean ball, then it's self-polar and the product is 1. The lower bound is is deeper, and we now know several proofs from this fact due to Bourgain-Millman, Kuperberg, and Nazarov. And here we don't know what is the worst case. We believe that the minimum of this quantity should be achieved when K is a simplex, but we don't know how to prove this. Okay, so we can remember that this volume radius dualized nicely. Now let me introduce another notion, which will be often easier to compute. So it will be the concept of mean width. So what is the width of a convex body? So it's a quantity which is dual to the gauge. So you fix, let's say you fix a unit vector theta from the sphere, and you want to, the width in direction theta is simply this distance between the supporting hyperplane in direction theta and the hyperplane passing through the origin. So we could say it's the half width because you only look at half of this red strip. And as I said, it's a quantity which is dual to the gauge. So the width of k in direction theta is the gauge of k polar. And if you want to formula, it's this one. You take this, the width of this strip is equal to the maximum inner product of theta with a point from k. Now, what is the mean width? So instead of looking only in a fixed direction, I'm going to take an average over all directions. So average with respect to the uniform measure on the sphere. W of k is this average of W of k theta over theta. So you have to compute an integral on the sphere, and it's because the quantity you integrate is one homogeneous, you can always do this by switching to the Gaussian model. So this is what I wrote here. Introduce G, which is a standard Gaussian vector in Rn, and you can compute the mean width of k as this expectation of this maximum of inner product of G with an element of k. Simply, if you do this, you have a normalization factor which comes out due to the fact that the Euclidean norm of a Gaussian vector is of order square root of n. So you have to divide by this expectation. Now there is a strong connection between volume radius, namely there is a simple inequality which is called horizon inequality, which says that for any convex body k, the volume radius is bounded from above by the mean width. So for example, if you look at the Euclidean ball, both quantities are equal to 1. But in general, this inequality should be compared to the isoperimetric inequality, because you can reformulate it as follows. If you fix the volume of a set, the convex set, then the mean width is minimal exactly when this set is a Euclidean ball. And the surface area also is minimal when k is Euclidean ball. It's the usual inequality is parametric inequality, and both are closely related. So I just here plotted a table where I displayed the classical examples of convex bodies and what are the values of these different radii that we may associate to them. So the first column, the in radius, is the radius of the inscribed Euclidean ball. The last one, the out radius, is the radius of the circumscribed Euclidean ball. And in between, you have this volume radius, which fills the volume, and this mean width. So for the Euclidean ball, everything is equal to 1. The second line is the unit ball for the L1 norm. So it's an octahedron in dimension 3. And you see that the out radius is equal to 1 also. The in radius is equal to 1 over square root of n. And the volume radius is comparable to the in radius. And the mean width is only slightly larger by a factor of square root of logarithm. The third line is the cube, which is dual to the L1 ball. In that case, the out radius is of order square root of n, and you see that both the volume radius and the mean width have the same order. And the last example is the regular simplex, which somehow mixes the behavior of both the cube and the L1 ball. So in each row, quantities increase from left to right because of the horizon inequality. And you see that on these examples, in each case, the volume radius and the mean width are comparable. Maybe there is a logarithm, but they are comparable, whereas they may be very different from the in radius or the out radius. So this cannot be true in general, because it's easy to imagine that if you look at a convex body which has volume 0, at a convex set which has volume 0, then it will have non-zero width. So you cannot hope for converse inequality in general. But in this example, there is some converse which is true. Now, I plotted this table because I want to show, to try to compare some sets which come from quantum information with respect to these more standard sets. Okay, maybe any questions so far? So now I'm introducing the set of states. Let me look at Cn, and the set of states on Cn, I call it D. So we know that it is a convex hull of all the pure states, which are the rank 1 projectors on Cn. And so what does it look like? So if I want to compute, say, the mean width of the volume, I have to precise which Euclidean structure I use. And of course, I will use the one which comes from the Hilbert-Schmidt inner product, trace of AB. And also, this set is non-symmetric. I plotted here, it looks rather like a triangle. There is a point which is somehow the center, which is the maximally mixed state, identity over n. And this plays the role of the origin when we perform convex geometry in this space. For example, here I wrote the formula that the polar of D is equal to minus ND. So in this formula, polarity and homothetic enlargements are taken with respect to the maximally mixed state as the origin. So this is simply a reformulation of the fact that the positive semi-definite cone is self-dual. Now this set is non-symmetric, which means that if you start from the maximally mixed state, and if you walk towards a pure state, the segment here is much longer than if you go backwards by a factor of n minus 1. So except for n equals 2, when you get the block ball, you get a set which is non-symmetric. And this is somehow an issue sometimes. So I will claim that this set looks like a simplex, and this is easy to believe. But simply, let me compute the volume of this set as a consequence of these Santalo and dual Santalo inequalities. So this inequality was true for any convex body K with centroid at the origin. So the set of states has indeed center of gravity at the maximally mixed state. And because the polar of D is minus ND, and because the volume radius is 1 homogeneous, a factor of n comes out, and you come to the conclusion that the volume radius of D is of order 1 over square root of n. So in this case, actually, it's a bit an overkill, because it's possible to compute exactly the volume of D, because it's a simple enough set. It was computed by Tchaikovsky and Sommers, so it, of course, agrees with this estimate. And one can show that the mean width is also of the same order, 1 over square root of n. But I want to say this because now I will consider a set which is more complicated, and for which there is very few hope to be able to compute exactly the volume. So we will have to do such approximate estimates. Yeah, so I'm come to this more complicated set, which is the set of separable quantum states, which I denote by S. So S is a subset of D, and it's defined, so if you don't know what entanglement is, here is the definition. S is defined as the convex hull of only pure states which corresponds to product directions. So inside CD tensor CD, now you look only at product unit vectors, and you take convex hull of this set. You obtain a set which is, of course, smaller than D, at all states. But it's remarkable that still the set has full dimension. Dimension of S is equal to dimension of D. And this would be false over the reals, for example. So this defines entanglement because we define an entanglement, we define a state to be entangled if it does not belong to this set. So maybe I may draw a picture. So in CD, tensor CD, this are the pure states. So it corresponds to the projective space of dimension d squared minus 1. Then this is the convex hull. This is a set of all states. Now, if I look only at a subset, a subvariety which corresponds to product vectors, so it's something which is of lower dimension. If I take convex hull, I obtain the set of separable states. And here in between there is the state identity over d squared, which is the centroid of this set and which is the maximally mixed state. Now, so as I said, these sets have the same dimension. And even more is true, Bardum and Gurwitz proved that they have the same in radius. So the Euclidean ball which fits inside D entirely consists of separable states. So it's not the case on this picture, but you have to imagine this. And today I would simply explain how to compute the volume radius and the mean width for this set, so which is plotted in red. So for the set D, we just show that in dimension n, the set D has volume radius of order 1 over square root of n. And here, because n is d squared, this is why this 1 over d appears. So now I will explain this mean width estimate. Mean width and volume estimates. So let me just have a slide to explain how to estimate the volume of a polytope. So, and later, of course, we don't have a polytope here, but we will be able to approximate by a polytope. So how to estimate the volume of a polytope? So suppose you have a polytope P inside the Euclidean ball, and you want to know how large can be its volume if you only know how many vertices it has. So with a polytope P with V vertices, how large can be the volume? So first, you have to have at least n plus 1 vertices to have non-zero volume, obviously. If you have exactly n plus 1 vertices, then the volume of P, then P is a simplex, and the volume of P is maximal when P is a regular simplex. So this is easy to prove. And in that case, the volume radius is equal to is of order 1 over square root of n. Now, if V is not too large, it's proportional to n, you may try to write down a union-bound argument. So what you can always do, so you have your polytope P, and by Kara-Theodory's theorem, you know that any point from P can be written as a convex combination of only n plus 1 points from the vertices. So you may simply write P as the union of all simplices which you build from vertices of P. So this looks huge, but because this volume is n homogeneous, as long as V is proportional to n, it still gives a reasonable bound. Now, if V is much larger than n, then this will be really bad. In that case, you should use the Urizen inequality and actually bound the volume radius by the mean width. And for the mean width, the union bound argument will lead to something which is sharp. So I just quoted a very basic fact from probability. If you take Gaussian variables with variance 1, and n of them, and if you look at the maximum, the expectation is bounded by square root of 2 log n. And this square root of 2 log x function is the inverse function to the exponential x squared over 2 which appears in the Gaussian density. So it comes from here. And remember that the mean width could be at the Gaussian version, could be computed using Gaussian variables. So if you write down this argument, you are led to this bound on the volume radius of P, square root of 2 log V over square root of N. And this is sharp, for example, for the cube. So if you take the cube inscribed in the Euclidean unit ball, it has 2 to the n vertices. So this bound is of order 1, and it is sharp. So in this case, it's reasonable. So now the idea is simple. You simply replace S by a polytope. So how do you do this? So here you have this blue set, which is a set of all pure states in product directions. So you will simply take a finite subset which is dense enough. So namely what we call the epsilon net. So this means that any point should be epsilon close to one point from this epsilon net. And you may take an epsilon net inside the extreme points of S, inside the pure product states. For fixed epsilons, for example 1 over 10, if you do this, you obtain a polytope with only constant to the d vertices, which is close enough to S. And here the constant to the d comes, this d exponent is the dimension of the manifold that you took the net inside. So this set of pure states, of pure product states with is sometimes called the Segre manifold. So if you use this bound from the previous slide for P, so you obtain a bound on the mean width of S, which is comparable to the mean width of P, which is square root of log of C to the D over square root of the dimension, which is here D to the 4, because we work with matrices over CD tensor CD. So dimension overall is D to the 4. And this is where this D to the minus 3 half factor comes from. Now, there are some issues here, notably due to asymmetry. And the correct argument requires some extra step when you symmetrize the set, but I won't talk on this. And also, it shows that this argument shows that this is sharp in the sense that there is a matching lower bound. Okay, so now that we keep in mind this estimate, I will connect it to the initial problem. So what was the problem? We had a pure state on a tripartite state, CD tensor C tensor CS, and you took the quantum marginal, forgetting about the CS part. And I wanted to show that rho is typically entangled when S is smaller than d cubed. So how do you show that the state is entangled? So entangled means not in this blue set. So by the Hahn-Banach separation theorem, it's enough to produce an hyperplane which separates your state from this convex set. And in quantum information, we call this an entanglement witness. So we have to produce an entanglement witness, which means an operator A such that if you compute trace of A rho, you obtain something which is strictly larger than the supremum of trace of A sigma over all separable states sigma. So if this is true, then rho cannot belong to the convex hull of to the set S. But in general, it's hard to check if a set is separable. And one reason for this is that there are many witnesses to try. You have to typically try exponentially a large number of them. So I claim that in our situation, we are able to bypass this issue by testing only a single witness. So, but this will only work for generic case, for the generic states. So this may sound surprising because it is known that estimating the gauge of S is a hard problem from the algorithmic point of view. But still, our approach will be sharp, possibly up to logarithmic factors for generic states. Okay, so what do I mean by testing a single witness? So I have to choose a good choice of A. So imagine that S was round, was Euclidean. Then to separate a point from the Euclidean ball, you simply have to choose an hyperplane which is orthogonal to the segment which links your point to the center of the ball. So this is what we are going to use. We are going to use as a witness the state rho itself, or rather rho minus identity over d squared if you want to have a trace zero operator. So this would always work if S was the Euclidean ball, and this will be typically bad in low dimensions. But in high dimensions, there is somehow a dogma that everything looks round if you look at it locally. So maybe the most famous result is the Dvoretzky theorem, which explains how high-dimensional convex bodies look locally round. So let me state it this way. So here it's in the Millman formulation of Dvoretzky's theorem. So let K be a convex body in Rn, and there is this assumption that K is not too degenerate. So this is technical, but let me just say that you can always reduce it to a situation by applying some well-chosen affine transformation. So you can always put every convex body in this not too degenerate position. So assume this holds. Then if you look at the projection of K onto a subspace of dimension which is of order log n, as compared to the ambient dimension which is n, if you look at the projection of K, then what you see, if you choose your subspace randomly, is something which will be very close to Euclidean with large probability. So you will see a convex set which will be sandwiched between two Euclidean balls of very comparable radii, which will be both close to the mean width. And there is a dual statement which is that if you look at the section of K with a subspace, again of same dimension, you also obtain something which is close to Euclidean ball. So here's a picture. If you start from the cube and you cut it in an oblique way, you may obtain an hexagon, which somehow is closer to the circle than the square was. So but it's really a statement about high dimensions. So. And you prove this by proving that this width functional satisfies some concentration properties. Okay, so this explains why this philosophy of reducing to the run case is maybe not hopeless, and actually it will work. So now I have to show that if I choose as a witness the state rho minus identity over d squared, that this strict inequality holds. So rho is random, so randomness here appears in both sides of the inequality. The right-hand side is the trace of A squared, and this is a very basic question about random matrices. So you can easily expand it moments and find what the exact value. It will be of order 1 over S. Now the left-hand side involves a supremum over separable states, which is typically hard. Actually, the left-hand side is exactly the width of S in the random direction A. But if you compute the average, it will be something which will be very close to the mean width, except that the randomness is no longer spherical or Gaussian, but comes from these quantum marginals. But still, the same approach works. You may also approximate S by a polytope and have this bound with, again, this factor d to the minus 3/2. And the key is that the tails are comparable to the Gaussian tails, what we call the sub-Gaussian property. So you just have to ask when this is smaller than that, and you see that it holds when S is less than d cubed. So this shows that in that range, quantum marginals generically are entangled. Yes. Okay. So in the remaining minutes, I will just compare this result to a result involving the partial transpose criterion, which is something which is often used as a relaxation to this separability entanglement dichotomy. So as I said, this answering the question whether a state is inside this blue set is hard. So here I will present an easy way to check a relaxation of this question. So what is the partial transpose? So you have a state on CD tensor CD, and you consider only transposition applied to one of the factors, let's say the first factor. Then you obtain what we denote by rho gamma, and we say that rho is PPT, positive partial transpose, if rho gamma is a positive operator. And if you think as operators onto tensor products as block matrices, this corresponds to transposing inside each block. So it's simple to show that if you start with a state which is separable, then this partial transposition is positive, so separable states are PPT. And this follows from the fact that this partial transposition preserves the product state. And converse is false except in very low dimensions. So you can ask the same questions about when quantum marginals are PPT. And in that case, because checking this PPT property is something which is easy algorithmically, I obtained a very sharp answer for the threshold. The threshold occurs at the level of 4d squared. So here you see we have more information. We know not only the order, but even the constant in front of the order. So similarly, below the threshold states, random states are typically non-PPT, and above they are typically PPT. And the proof goes via random matrices. You have to compute the spectrum of the Wishart matrices, which I defined before, on which you apply this partial transposition. So you can identify the distribution, which will be a non-centered semicircle distribution, and you obtain this values of the threshold. Now, some consequence, which is interesting from the quantum information point of view, is that there is a range of parameters when you are between the two thresholds, for which your quantum marginals are typically entangled and PPT. So this means that these states are non-distillable for people who know this, and this shows that these states, which are called bound entangled, are somehow generic. Okay, so to conclude, I will just summarize what I showed you. So we identified the range of parameters for which quantum marginals are typically entangled. So again, this makes sense only in the large dimension limit. And this was done by computing some parameters associated to the set of separable states, and especially the mean width. Now the computation itself is simple. It's basically a union-bound argument. Another fact is that in the typical situation, the obvious witness is enough to detect entanglement. So something I did not show is that beyond this threshold, outside this range, there is typically no entanglement. But as I said, this will be covered tomorrow by Staszek Szarek. And to conclude, if you combine this with other results, you may obtain the information that some classes of states, such as these bound entangled states, which you could think of pathological, actually are generic in some regime. Okay, so thanks for your attention.
When you started, you said the threshold was extremely sharp. It changed 2 qubits made a difference. This
Yeah.
doesn't follow from what you showed.
No. This is right. Yeah. I only showed a crude argument. Yeah. So this also will be covered by Staszek's talk.
You had Alice's dimension and Bob's dimension the same. Is it easy enough to generalize to when they're different?
Yeah. So if as long as they both go to infinity, what will only matter is their product, mostly. So say you can have, I think, flexibility on this. You may allow one to be going to infinity slightly faster than the other. If you look at a completely unbalanced situation, then it will be a different picture. If both go to infinity reasonably comparatively, then it will be what will enter will be the product of the dimension, so only the global AB dimension.
Have you thought much about multipartite separability?
Yes. So again, it depends on what asymptotics you want. If you want like tripartite with large dimensions for each factor, then the same argument works. If you want many qubits, then I don't know. And in that case, the point is that we don't know how to compute. Okay, we know how to compute the volume, but we don't know how we can come with this argument shows some bound which we don't know whether it is sharp or not, and probably it's not. So yeah, but for fixed number of parties, it works the same.
So if you have many qubits, the difficulty is you don't know how to find a good entanglement witness.
So this works in some range.
Yeah.
But probably it's not optimal. Yeah.
Further questions? If not, let's thank the speaker again.